Okay, welcome back to what I think might be your last video of this remote learning. Maybe not. We'll see what the final week looks like. So just a quick recap, we were looking at the Tarzan problem, and you were tasked with 3 through 7 on your own. So whether you were able to figure those out pretty easily or whether you attended the office hours was totally up to you. The ones that I would like to look at before going much further are 6 and 7, because 6 and 7 lead us to number 8, which is where we're going to start. 6 says, how can you determine the points of greatest velocity and smallest velocity? So remember, velocity is going to be how her distance from shore changes over time. So how can you predict the greatest velocity and smallest velocity? By inspecting the graph of d of t. So that's number 6. So I'm looking at d of t. And remember, we had talked about how distance is changing over time. If you look at this function, as you can see here, her distance is not changing very fast over time to begin with. And one thing we can do is we can draw in that tangent slope here. We can see that her distance is changing. That is a slight positive, but it's not changing too quickly. If I move along a little bit, I can see that now my slope of my tangent line is more positive as we go. But if I zoom in here a little bit, what I do know is that as I travel up towards the peak of her swing, once again, the slopes of those tangent lines, they increase for a while, but then they start to decrease again. So the point at which her velocity was greatest is going to be right here at this inflection point, at that change in that concavity where concave up changes to concave down. Why does it change? Well, it changes because this point right here is going to have the greatest positive velocity. So her velocities are increasing, and then they start to decrease, which is going to change the concavity. So if this is the point of greatest velocity, then that also occurs here during her second swing, which means her greatest points of velocity are going to occur at 2 seconds and then also again at 10. So you can explain something. So that is going to be a time of 2 and a time of 10 seconds. And I would say, inspecting the graph, you can see that the slopes of the tangent lines at a time of 2 and 10 seconds are the greatest positive slopes. Okay, so again, a graph question. How can you determine when the velocity is 0? By inspecting the graph. So even if we don't know anything about this situation, I know that how distance changes over time is going to be measured as velocity. So according to this graph, the slopes of the tangent lines is going to be 0 right here at the peak of her swing. So you'll get a velocity of 0 right there at 4 seconds, which means, of course, it's going to happen here. 0 velocity at 12 seconds. And then, of course, as she goes back in her swing, that will also happen. She will have tangent line zeros at 8, 16, and also to start. So the slope of the tangent line at those points is going to be 0. So I would say something like that. I'm going to skip through that. You can do that on your own, or you can push pause and go back and fill that in. Okay, so question number 8, I'm going to walk you through 8, and I think that's it. You're going to make your graph number 9 on your own and continue onward. So number 8, though, let's approximate the velocity. So now that we know that the largest velocity is here, oh, I forgot smallest velocity. What am I doing? I miss you guys. I usually catch all my mistakes. So this negative velocity here would be our smallest negative velocity. And you can add that in there. So that would be at 6 and also at 14. Okay, so question 8, approximate the velocity using two-sided estimates at the times determined to be the greatest. All right, so now that we know that our greatest happen here and those other times are 0, we need to start making sense of what's going on with velocity. So we know velocity has very important points at 0, then again at 2, then again at 4 and 6 and 8. These are when velocities are the most interesting. So the greatest velocities are going to happen here, and we need to actually approximate the velocity at that time. We know it's going to be positive, but we don't know what it is. So I'm just going to take a little pause, and I'm going to go back to our ball lab situation just to give you a little refresher. So I made up a ball lab situation here. At 0 seconds, the height of the ball was 3. After 1 second, it's way up there at 50. After 2 seconds, well, that rate is still increasing, but that rate of change is not quite as steep. So when I'm looking at something like this, I'm going to clue in here at time of 1. If I was trying to estimate the velocity of the ball at 1 second, remember, nothing changes at one point in time. So I need to select a time just before 1 and select a time just after 1. And that's going to give me an awesome approximation for my slope at 1 second. So if I were to choose a point just after 1, I mean, I could choose 1.5, but I feel like I could do better than that. So what if we do something like 1.1? You could even do 1.01. All right, just before, how about we're just going to go 0.9. So then at this point, you would have to use the equation to figure out the height. It's going to be just above 50.2 and just below at 0.9. And then you can find that rate of change with the height minus the height divided by time minus time. And that will give you the rate of change at 1 second. All right, that was a little refresher there. So let's think about the Tarzan lab here. If I'm going to do velocity, we already have a little table set up for you. So if I think about the greatest point in velocity, there are 2 points in velocity where it's the greatest, when she's at the bottom of her swing. So we're looking at 2 seconds or 10 seconds. Doesn't matter which one you choose. I'm going to choose 2 because the lower the number, the less scary it is. So if I've got time here and I'm trying to map the change in distance over time so I can get that first rate of change. So I know that I'm trying to clue into 2 seconds. At 2 seconds, I know her distance away from shore is 35 feet. I know that just before 2 seconds, her distance is going to be less, and just after 2 seconds, her distance is going to be more. So as we were talking in the ball lab, we know that a good point to choose before would be about 0.1 second before, and then a good point after would be 0.1 seconds after. Well, so now what we have to do is we have to try to figure out what is that distance away from shore at 2.1 and 1.9. Well, we don't really know, and you can't just guess. That's not good enough. However, we do actually have a function. We know that distance at a certain time is going to be modeled by your periodic function, -15, cosine pi over 4 times time plus 35. We found that last time. So now I've got an input of time where you can now input 1.9 or 2.1 and figure out these outputs. So if I were to input 1.9 into this function, or better yet, I could graph the function and use my table of values. So let's say I'm going to put 1.9 right in there. So I need to make sure that I am in radian mode. So there I am, mode. This time I'm going to be in radian mode because I'm using pi over 4. And I'm going to input 1.9. So I'm going to do everything one step at a time just to make sure that my order of operations haven't messed up at all. So I'm going to take pi divided by 4, and I'm going to multiply that by, actually it's a little bit easier if I do 1.9 times, just want to always make sure, depending on no matter what calculator I have, that I am multiplying that whole fraction, pi over 4 times 1.9. You never know. All right, so I get that number. I'm not going to write this down. I'm going to leave it in my calculator. I need to take the cosine of that number. So I'm going to take the cosine of that number, enter. Now I need to multiply it by negative 15, enter, and add 35. So this should be a number, remember, at 1.9 seconds, she is not yet to 35 feet away from shore, which means it should be slightly less than 35 feet. I'm going to say 33.82 or 823 works great for me. So we've got 33.82. She's not quite to 35. You can do the exact same thing with 2.1. And when you do that with 2.1, you end up with 36.18, which we know is slightly after 35. All right, so at this point, using these 2 points, we can estimate the slope of that line at 2 seconds. So remember the slope of the line, y2 minus y1. So I'm looking for my velocity, actually at 2 seconds, is going to be 36.18 minus 33.82. So she changes that many feet in 2.1 minus 1.9 seconds. And if, in fact, that's what you do, this ends up being 0.2 seconds, you will end up with 11.77 feet per second. That is as fast as she's going. That's pretty fast. 11.77 feet per second at this point, which means also she's traveling that fast at this point. Okay, so now we can start to make a table of values here for velocity. Okay, so time and velocity at a certain time, which of course is going to be first rate of change for this particular function. So I know important points for my graph are going to be time of 0, her velocity is 0. Slope of that tangent line is 0. The next important point are going to be at my 2. At 2, I know that her velocity is 11.77. Okay. Then again at 4, her velocity is 0. I'm just following my graph. After 6 seconds, what do you think her velocity is going to be right here? You could double check just to make sure, but of course it's the exact same negative velocity as her greatest. She's just going in the opposite direction. And then after 8 seconds, she's at the peak of her swing. Sorry, she's all the way back and she's at 0. And then the process repeats itself all the way to 16. Okay, so your task now is to graph velocity over time for the same interval. So if you're using this graph paper, you can tell that velocity is right here. Again, we have the same intervals so that you can compare your function with the first rate of change, just like we did in the ball lab. And then the process will repeat for the second rate of change. So how fast something is changing, how fast the speed is changing over time will give you that acceleration. Okay, this is your task. Attempt to finish this activity, and if you struggle, we will see you at our office hours.